Hello everyone. In this lecture I shall discuss the analytic function and its connections with the differentiability. Actually, this topic analytic function is most important in complex analysis. Rather I say it is the pillar of the complex analysis. The complex analysis rests on analyticity. Okay. So this important concept of analyticity should be understood in a very clear manner. As the definition of analyticity is based on the differentiability, so let me to recall the differentiability of a function. Right, we say a function fz is differentiable at a particular point z0 if f dash z0 exists. Okay, f dash z0 exists. So as you have written z0, no need to write exist at z0. F dash z0 exists means f dash z exists at z0, and we write it by using the ab initio method or first principle as you read in your real functions. So limit z tends to z0 fz minus fz0 by z minus z0. If I substitute z minus z0 is equal to h, I can rewrite it in that way, right? So now we say f dash z it is differentiable at a particular point. Now when it is differentiable in a domain, right? If f dash z exists everywhere at every point in a domain D, right, then we say f is differentiable in the domain D. Clear? This is restricted to a particular point and it is restricted to all point in a domain D. That means we say f dash z is equal to in general limit h tends to 0 f of z plus del z f of z plus h minus fz divided by h exists for all z in D, right? For all z in D. This also sometimes this h we may write it del z, no issue. Now instead of h if I write limit del z tends to 0, right? F of z plus del z minus fz divided by del z. So exists for all z in D. Now here this del z can be viewed as, what is this del z means? This is also a complex number, means we can write it del x plus I del y in that way. Here also this h is a complex number, right? In that way we have to interpret. If here I write h should be of the form p plus iq, in that way. These are all complex numbers, so in any way you can write. Now we should discuss the most important concept of analyticity, right? Analytic function. This definition is most important. So now, before the details of the discussion on the analyticity, let me to introduce myself. Professor S.K. Paikray, Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology in short Visut, Burla, Sambalpur, Odisha, India. So now let me to discuss the definition of analytic function. Now coming to the definition of the analytic function, as I have mentioned, differentiability at a particular point and differentiability in the entire domain. So likewise we will see the analyticity at a particular point. A function fz is said to be analytic, right? Analytic at a particular point z0 if it is differentiable at z0 as well as at every points in the neighborhood of z0. So here in complex analysis, by saying the neighborhood of z0, what does it mean? It is this open disk consisting of z0. It is not only at z0 but also at every points in the neighborhoods. Also it has to be analytic here, differentiable here, at every points in this neighborhood, right? Merely at a particular point z0, if it is differentiable, we cannot say this is analytic. So that means we need, for analyticity, we can rewrite this definition as, this is most important definition, we can rewrite it: fz is said to be analytic at z0 if it is differentiable not only, right, I write not only at z0 but also in some neighborhood of z0, right, but also in some neighborhood of z0, right? So merely the differentiability at a particular point doesn't imply the analyticity. It has to be analytic at z0, right? So fz is, so what does it mean? Or we can write a single valued function. These are all single valued function, right? A single valued function fz is said to be analytic at z0 if there exists a neighborhood, you say z minus z0 mod less than delta, neighborhood of z0 such that f dash z exists, right, at all points in the neighborhood, at all points in the neighborhood, right, exists at all points in the neighborhood. So that means not only at z0 but also at every points in the neighborhood, right? So now, so to summarize, I can say, so that means I can say, so thus roughly we can say, roughly differentiability at z0 plus, right, differentiability at all points in the neighborhood of z0, this implies analyticity of fz, at z0, okay? Now if I write differentiable only at z0, right, doesn't implies analyticity of fz at z0. So merely at a particular point doesn't imply the analyticity. And however, if fz is analytic at z0, then we can write this double implies also, differentiability at z0 plus at all points in the neighborhood implies analyticity, and vice versa also. Analyticity at z0 means differentiable at z0 as well as differentiable at all points in the neighborhood of z0, okay? Next, like the differentiability in a domain, right, at a point in line we discussed the analyticity. Now differentiability in a domain, likewise we have the analyticity in a domain. Now coming to the analyticity in a domain, so roughly we can say if fz is differentiable everywhere in a domain D, then fz is said to be analytic in D. So in this case, the analytic in a domain is same thing as differentiability in the domain. So in this case, analytic in a domain, right, in a domain, analytic is equivalent to, right, analyticity is equivalent to differentiability. But in a particular point, at a particular point, right, this analyticity is not equal. It is not equal, right? It is not equal. So in a domain, this analyticity is equal to the differentiability. So the property of the differentiation will work for the analyticity, right? So the property of differentiation also work for analytic function in a domain, right? But not at a single point, right? But not at a single point. Clear? Thus we say in a domain D, if F and G are analytic, then F plus G, F minus G, F dot G, F by G with G not equal to 0 are also analytic. And the further properties also, and further properties also. The polynomial function is analytic, right? Polynomial function is analytic. So the differentiation property will work here in a domain, right? But while at a particular point, it is then restricted, right? Here it is restricted. Now this discussion, roughly we discuss it. Now if we come to the exact definition here, right, we say the exact definition, we say if f dash z exists at every point of a domain D except at a finite number of I say exceptional points, then fz is said to be in short I write STB, said to be analytic in a domain D. Okay, means we can exclude some finitely many points, then also we say it is analytic in a domain. Now these exceptional points, okay, these exceptional points are called singular points. Okay, so these exceptional points are called the singular points or singularities of fz. Okay, so that means for differentiability it must be differentiable at each point, at every point in the domain. But for analytic in a domain, we may exclude, right? We may exclude some finite number of points, right? Then also it is analytic. You see the key difference here. For I repeat, for differentiability in a domain, I need, and it is differentiable at each point. So you see the key difference here. For differentiability of fz in a domain, it needs differentiability at each point in the domain. However, for analyticity in the domain, it needs to be differentiable. It needs to be differentiable at, I can say, almost all point. Almost all points, right, in D, except, you mark, except some finitely many points, except some finitely many points, okay, except some finite number of points. So this, thus the analyticity has the broad aspects than the differentiability, right? In that context, this analyticity is broader than your differentiability, right? So thus we can say the analyticity has broader aspects. It is more broad than differentiability, right? Because for differentiability it need at each point, but here except some finite number of points, right? And in this line, if it is analytic at every point, then there is a term, it is called the regular. So now as you see, in analyticity we may exclude some finite point, but if it is like differentiability, if it is differentiable at each point, likewise if f dash x exists at each point, we call it regular, right? We call it regular. Instead of analytic, we call it regular. However, this regular or holomorphic are used the synonyms of analytic, okay? Sometimes we call these analytic functions, keeping these very small differences in view. Yes, analytic function is same thing as holomorphic function, is same thing as the regular function, okay? So now this regular and holomorphic, right? This is regular is one definition, holomorphic is another definition, and analyticity is another definition. However, these three can be used as synonyms, right? Now what is singular point? Singular point means a point z0. A point z0 is said to be a singular point of fz if f dash z0 does not exist, right? Means that is fz is not analytic at z0, right? If fz is not analytic at z0, then z0 is a singular point, okay? So if it is not analytic at z0, then we call it is a singular point, right? So the word regular, the word holomorphic are the synonyms of analytic. And we have one more, and subsequently this singular point are classified. These singular points are classified into many aspects, okay? These singular points are pole, removable, and essential, and so later I will discuss, okay? But here we have another definition is meromorphic function. Now coming to the another definition of meromorphic function, a complex valued function fz is said to be meromorphic if it is holomorphic, or we call it analytic, holomorphic or analytic. If it is holomorphic, or what we call it analytic everywhere, okay, everywhere except at isolated points. And these isolated points are called poles, and these isolated points are called poles. So you see, this meromorphic is also maybe use also the synonyms of this. Sometimes the term regular and holomorphic and meromorphic also I can say, and meromorphic are used as synonyms of analytic function. Okay, analytic functions, right? So now coming to the definition of entire function. A function which is analytic everywhere, okay, means at each and every point in the complex plane, in the entire complex plane, in the whole complex plane, is known as an entire function. Sometimes we also call it integral function, right? For example, e to the power z, it is analytic everywhere, it is differentiable everywhere. Polynomial function of pz, a0 plus a1z a2z square an z to the power n, positive integral power of z, right? These are the integral functions. Sin z, cos z, these are all the examples of the entire function. These are analytic everywhere, right? And the we can say pz by qz, quotient function with qz is not equal to 0, right, is also an analytic function. So these are all analytic functions. Being it is analytic everywhere, these are called the entire function. So now this meromorphic function, as I have told, it is also synonyms of the analytic function or holomorphic function. Okay, so the critical differences should be understood, right? So now coming to some solved examples. So coming to example 1, so that fz is z to the power n is analytic everywhere for all non-negative integral power of n. Means non-negative means here 1 z square, like that. These are all analytic function, and these are in fact the entire function. If we want to prove it, let fz is equal to z to the power n, implies f of z plus del z is z plus del z to the power n, binomial expansion. So this is equal to z to the power n plus nc0 z to the power n minus 1 del z plus nc1 z to the power n minus 2 del z square, and plus it will continue del z to the power n, right, del z to the power n. So now what is your f dash z? F dash z is equal to limit del z tends to 0 f of z plus del z minus fz divided by del z. So this is equal to limit del z tends to 0 here z to the power n plus it is n z to the power n minus 1 del z plus n into n minus 1 nc0. Just 1 second, there is a correction here, it is nc1. So here this is the expansion, binomial expansion. So this is actually nc0, this is nc1, this is nc2, like that, this is ncn. So this will be here z to the power n plus n z to the power n minus 1 del z plus n into n minus 1 by 2 z to the power n minus 2 del z square plus del z to the power n, and minus this fz is here, z to the power n. So this z to the power n, z to the power n cancel, divided by del z. So now you can take del z common throughout. So this is equal to limit del z tends to 0, here taking del z common, here n z to the power n minus 1 plus n into n minus 1 by 2 z to the power n minus 2 del z plus on here plus del z to the power n minus 1 divided by del z. Now del z cancelled here. Okay, so now putting del z equal to 0, now these are all 0. So what we are getting? We are getting n into z to the power n minus 1. So this is exists. So therefore here f dash z here is n into z to the power n minus 1, right? Exists for all z, So this implies fz is analytic everywhere or differentiable everywhere in the neighborhood of z. So this implies we can say also fz is analytic everywhere in C, right, in C. That's why all polynomial functions are analytic, right? In a remark we can write polynomial function fz is pz is a0 a1z plus up to anz to the power n is analytic. Here pz by qz with qz is not equal to 0 is also analytic everywhere. So coming to example 2, we see that fz is z plus z conjugate is not analytic everywhere. If any function involving z conjugate is not differentiable and not analytic. So if you want to prove it, okay, what is your f dash z is limit z tends to z0 at a particular point, say z0, fz minus fz0 divided by z minus z0. So this is equal to, I can write limit z tends to z0. Here fz is z plus 2z conjugate minus fz0 is z0 plus 2z0 conjugate divided by z minus z0. So this is equal to, you can write limit z tends to z0. You just collect it in this way, z minus z0 plus 2i's z bar minus z0 bar divided by z minus z0. Now separating the terms here, you are getting limit z tends to z0, this by this is your 1, okay. So this is your 1 plus 2i's z bar minus z0 bar conjugate divided by z minus z0 conjugate, only z minus z0. So now if this z minus z0, suppose I write z minus z0 is equal to some capital Z is equal to, suppose, some capital X plus capital IY, then what I am getting, this is equal to 1 plus 2i's limit z tends to z0 or limit capital Z tends to 0, okay. Here z bar by z, and as we see this limit doesn't exist, okay. As we see 1 plus 2i's limit x plus iy tends to 0, right. Here x plus x minus iy by x plus iy, right. And what we have seen here, as we see along, if x is equal to 0, if your y is equal to 0, x tends to 0, means real path, purely real path, then what will happen, this limit is 1. And if it is x is equal to 0 and y tends to 0, imaginary path, purely imaginary path, then what will happen, this limit is minus i, right, minus iy by iy, minus 1. So once the limit is 1 here and minus 1 here, so this limit does not exist, right. So that means here f dash z doesn't exist, right, at z0, as choice of z0 is arbitrary, so it is not analytic everywhere. So in a note we can write it, here that note, in a write any function involving z bar, z conjugate is nowhere differentiable, so nowhere analytic, right. Coming to one more example. Now coming to this most important example, right, what I can say, very important example. Fz is z mod square is differentiable at origin, mark only at origin, not analytic there at, not analytic means for analytic what we need, for analytic what we need, differentiable at 0 plus differentiable in the neighborhood of 0, neighborhood of 0, but here it is analytic only at 0, we see now, right. Coming to the solution, let fz is equal to z mod square is z conjugate, right. Now what is f dash for at z0, at z is equal to 0, what is your f dash z, f dash z at z is equal to 0 is limit h tends to 0, or I can write is limit z tends to 0 fz minus f0 by z minus 0 here, because z0 is 0 here. So now this will be equal to here fz is zz conjugate, so this is limit z tends to 0 zz conjugate by z, so this is equal to limit z tends to 0 only z conjugate, so this is equal to limit x plus iy tends to 0 x minus iy, right. Or here we directly write it, here we directly write it, here it is 0, right, or we directly write it, here it is 0, so that means f dash 0 is equal to 0 exists. So this implies fz is differentiable at z is equal to 0. Now we see at z not equal to 0, okay, at z not equal to 0, at z not equal to 0, say at z is equal to z0 not equal to 0, what we can write here, so what is your f dash z0, f dash z0 is limit z tends to z0 f of z minus f of z0 by z minus z0, so what we can write here, so this is equal to, we can write limit z tends to z0 z bar minus this will be here z0 bar divided by z minus z0, so I can write it limit z tends to z0 z bar, I can subtract z0 z bar and I can add again plus z0 z bar minus z0 z0 bar by z minus z0. Now I collect these terms here, so this is equal to limit z tends to z0, I take z bar common, it is z minus z0 by, and plus here it is z0 taken common, z bar minus z0 bar divided by z minus z0. So now if I separate them out, so this is equal to limit z tends to z0, this by this means here z bar plus limit z tends to z0, this will be, so now here this by this it will be z0 is a constant here, now z0 can be taken out, it is z bar minus z0 by z minus z0, okay. If I put some z minus z0 is equal to capital Z, say, okay, then it will be what, limit z tends to z0 z bar plus z0 small z0 here into, right, this is your small z0, this is small z0 into limit z tends to z0 capital Z bar by z, as we see in the previous example, right, this as you see in the previous example, this doesn't exist, okay, because along real path what we are getting, it is z0 into 1 we are getting, along imaginary path what we are getting, it is z0 into minus 1, okay. So this doesn't exist here, this does not exist, so that means fz is not differentiable, fz is not differentiable, right, not differentiable at z0 not equal to 0, so that means clearly fz is differentiable only at 0, but not in the neighborhood of 0. So this implies fz is not analytic at 0, even if it is differentiable at 0 origin. Okay, so here coming to this definition of analyticity, coming to this here, differentiable only at z0, right? Differentiable only at z0 doesn't imply analytic. So for this context you can see one example. Fz is equal to z mod square is differentiable at 0 only, right? But not analytic at 0, right? So in this context we can have this example. Okay, now to summarize, let me to write some properties. Now before the conclusion we should have some important results. Fz is analytic if it is free from z conjugate. Set of all analytic points forms an open set. Fz is analytic implies Fz is differentiable in the neighborhood of a means uncountably many points. But the converse is not true, not conversely. Even if it is differentiable at uncountable many points, it not necessary that it is analytic, but at all points implies analytic. Fz is analytic, right? At all points implies analytic, but uncountable many doesn't imply that it is analytic. Fz is differentiable at countable many points. Likewise, it is not analytic. It is nowhere analytic, right? Now algebra of analytic function in a domain, that algebra of analytic function is same as the algebra of the differentiable function. So as you see now, analytic means defined and differentiable, right? Before differentiability we need the defined, but not defined, the contrapositive, not defined implies not analytic. Similarly, not differentiable implies not analytic. For example, if I say fz is equal to z by z plus or some k constant, real constant, is not analytic at z is equal to minus k, because the denominator is equal to 0. It is not defined, right? At z is equal to minus k. Otherwise it is analytic. Right? Coming to one more example, if I say fz is equal to z plus e to the power z, fz is equal to z plus e to the power z, it is analytic everywhere. Analytic everywhere, because this is analytic, sum of two analytic function is analytic function. If I said, if I write fz is equal to z into e to the power z, it is also analytic everywhere. Because product of two analytic function is also analytic function, right? If I write some fz is equal to x minus iy by x minus iy plus some k. Now is it not same thing as z conjugate by z conjugate plus k, right? Any function involving z conjugate is not analytic anywhere, means nowhere it is analytic, right? I write one more example. Fz is equal to z modulus fourth, right? Is differentiable but not analytic at z is equal to 0. Is differentiable at 0 but not analytic at 0. As we see in the previous example, we also see another example, z mod square. Okay, so these are the standard examples. So here fz is equal to z mod square is differentiable at 0 only, right? It is only at 0 only, but not analytic. Already we did it. Similarly, z mod to the power fourth. Okay, so now the important thing, as I have told, that analyticity is most important. It is the pillar of the complex analysis. We should carefully learn the critical aspects. Analytic function, also otherwise called the regular function or the holomorphic function or the meromorphic function. However, the slight differences are there. If we go into deep analysis, then that deep analysis is needed, that mild differences should be counted. Okay, so now at this juncture, my appeal to all of you, if you feel that this lecture is useful and interesting, please like and subscribe to this channel, right? Like and subscribe, which will boost my motivation. And most importantly, in next upcoming lecture I will discuss the Cauchy-Riemann equation, right, which is again most important, and I will connect the analyticity and CR equation. So the next lecture will be most important from this aspect. Okay, so with this we should conclude this lecture here. Thank you all. Have a nice day.